Okay, hi everyone. So today I will show you two example problems. The first one is about the Virial Theorem. I'll show you how to compute the virial mass of a gravitationally bound object. And the second one will be about how we can convert between the density distribution and the gravitational potential. Okay, so first, we'll be talking about Virial Theorem. And okay, so I believe like in the lecture, so professor have already derived the virial equation, which is very commonly used and simple equation in astronomy to derive the mass of a gravitationally bound object. So if an object is in virial equilibrium, which means that they are gravitationally bound, then, and if we exclude the external force in this system, then we will obtain a very simple equation that 2 times the kinetic energy plus the potential energy is 0. So this is the mean kinetic energy of the system. And this is the mean potential energy. All right, so this is our virial equation, and we use this to derive the mass of a gravitationally bound object. All right, so as I said, this is very useful to derive the mass. So as long as the target we are interested in is gravitationally bound, which is like most of the astronomical object is gravitationally bound, right? For example, the like the stellar cluster, or even like the cloud, the interstellar gas, it could be gravitationally bound, right, for interstellar gas. And that would be what we are interested in, because like a gravitationally cloud can like form stars, and that would be the region we're interested in. So in the table 3.1 of our textbook, there are plenty of data for many star clusters, and we can just pick one of them and see if we can derive their virial mass and verify that they are gravitationally bound or not. So we'll just randomly pick one of them. Let's say the M4 cluster. So based on the data, we measure the radial velocity dispersion, which is 4 kilometers per second, and the core radius is 0.5 parsec. And also the mass is 6 times 10 to the 4 solar mass. Okay, so since virial equation, if we exclude the external force, then the only terms we care about is the kinetic energy and the potential energy. And that would be related to the velocity dispersion and the size, the radius, right? So the only term we need will be these two, and then we can derive the virial mass of this cluster. And we can see if our derived virial mass is about the same as the mass measured in other approach. Then if they are similar, then it means this object is probably gravitationally bound. Okay, so let's start. So first we need the mean kinetic energy. So based on the ergodic hypothesis, the mean kinetic energy with time will be the same as the mean kinetic energy of all the particle in the system, right? So the mean kinetic energy will be 1/2 m sigma v squared, the average of sigma v squared. And since notice that for the measurement, we can only measure the radial component, which is the line of sight component of velocity dispersion. So to get a 3-dimensional velocity dispersion, we can assume isotropic motion. Then the sigma v squared will be 3 times the sigma r squared. And sigma r squared. Okay. And then we need the mean potential energy, which is the potential energy should be in the form of 1/2 and summing up all the potential of this system. It would be like 1/2 and summation of m phi in this system. And so this will be negative gm over 2 times the core radius. All right, so very simple. So by plugging in these two values into the virial equations, we can get 3 times, so we have 2 times the kinetic energy. So it's 2 times the 3/2m sigma r squared should be equal to negative potential energy, right? So that would be gm over 2r. Okay. And we can basically cancel out the m over here, and the 2 over here can also be canceled out. So we get 3 times the sigma r squared equals g over 2r. Gm over 2r. Oh, sorry, this is, the numerator should be gm squared. Yeah, that was my mistake. Because the potential term here includes an m, and to convert it into the potential energy, here is another m. So there's a m squared in the potential energy term. Okay, so by canceling out 1 m, so we have 1 more m left, then we can get the virial mass equal 6 times sigma r squared times radius over g. Okay. So this is the derived virial mass. Any questions so far? So let me know if I'm if this is too fast or too slow. Anything.
No, seems good.
Okay. Okay, sounds good. So we have derived the the formula of virial mass for this object, for this cluster. Okay, so based on the data on the textbook, we have sigma r is 4 km/s, and the core radius is 0.5 parsec. And what else? We also need the gravitational constant, right? So G is, based on the SI unit, G is 6.67 times 10 to the minus 11. Okay, this is in SI unit, which is, so the unit should be m cubed and s to the minus first. Okay, so let's plug this in. So we will have the virial mass of this object as 6 times sigma r squared is 4 squared, right? So that should be, so since we are working in SI unit, we should convert kilometer per second into meter per second, right? It should be consistent. All of the values here should be in SI unit. So we have 4 km per second is 4,000 meter per second, and we have 4,000 squared. And then we need the radius, and the radius is 0.5 parsec, but we have to convert parsec to meter, and that would need a conversion factor of 3.08 times 10 to the 16. And divide this by G in SI unit. Okay, so just to clarify, this should be in the unit of meter per second, and this term we convert parsec to meter. Okay, so if you do this calculation, then you will find the virial mass is 2.22 times 10 to the 34. But remember, we're working in SI units, so the unit here should be kilogram. And but since the data we have is in solar mass, we have to convert it to solar mass. And we know that one solar mass is about 2 times 10 to the 30 kilograms. So that would be this value divided by 1 solar mass. So this is in kilograms. And that would give us something in the order of 10 to the 4th solar mass. And since we have, based on the data, we have a mass of 6 times 10 to the 4th solar mass, right? So, so you will see that the virial mass we derive is pretty close to the mass given by the measurement. So it means that this object is gravitationally bound. And you can, so since there are plenty of data in your textbook, you can just also pick one of them and try this. You will find that the virial mass you derive should be at least at the same order of the mass measurement. So this should be reasonable because we know star clusters, of course, they are gravitationally bound. And so apart from calculating the mass of a gravitationally bound object, actually the more widely used way of Virial theorem is, so we can actually measure the mass of an object in many different ways. And the most commonly used way is by using the kinematic of the system. So if we know the velocity of the object, then we can derive the kinetic mass of that system, or we can use photometry to determine the density or column density and convert that to the mass of an object or gas or whatever. And we usually use multiple kind of approach to derive the mass of astronomical object. And what we can also do is we will also derive the virial mass of that object, and we can compare the mass and the virial mass, and to see if this object is gravitationally bound. So this is usually adopted in interstellar medium observations, because like for example, for star cluster, if we know that we already know it's a star cluster, then of course it's gravitationally bound, right? But for interstellar gas, we are not sure if the gas we're observing is gravitationally bound or not. So this is a useful way to determine if the gas is if it is really a cluster of gas under gravitational effect, or it is actually just a diffuse gas, but seems like it is a cluster. Okay, so this is the first part for the Virial theorem. Any questions?
Yeah, I have a question. In the course, professor told us about a parameter in the virial mass, the Eta parameter, and I was wondering when do we? I mean, there's not here, so I was wondering why.
Okay, Eta. Okay, so I think so. A very commonly represented form of virial mass is, I think the professor probably derived something like 6 sigma square eta r over g. Yeah. So this is a general form of the virial mass. So you can see the form we derive is here, and so there's an additional eta here in the general form, right? So this is because okay, so if we compare these two forms, you will get that eta is approximately 1, and this is true. But for different density distributions, so since we're now working on star clusters, and we can treat it like a system of point particles, we're actually treating it as a system of point particle. But if we're now looking at a cluster of gas or something, or even like a galaxy, so the density distribution can vary, right? The density distribution varying with radius, like it could have a uniform spherical distribution, or like a Plummer sphere, which is shown in your homework. So there are all kinds of density distribution, and the value of eta will depend on what kind of density distribution we're using. But in general, this value should be close to 1. But in details, it will vary, and we should account for that when we are applying different density distributions. Does that sound okay? Great. So I'll write it down. so this would depend on density distributions. Okay. Okay, so thanks for asking that question. This is, so since I mentioned the density distribution, this is very relevant to what I'm going to talk about next. So if there's no more question, I'll move on to the second part. The second part is about the conversion between density distribution and the gravitational potential, rho and phi. Okay, so this is density, and this is the gravitational potential. So in your homework problem, there should be one problem about, so the question gives you the gravitational potential form and wants you to obtain the density distribution form, right? So homework, you have given phi, and you have to show that the density form. Okay, so to relate density and gravitational potential, so I believe you already learned in class the Poisson's equation. So this is very useful in relating these two quantities. So that we have Laplacian equal 4 pi g rho, right? So if we have the gravitational potential form, then to obtain the density, we will just use this equation and get rho equal the Laplacian over 4 pi g, right? And yeah, so this is very simple. And to calculate this Laplacian, it should also be simple, but notice that the calculation of Laplacian would depend on what coordinate you are using. So coordinate. So like if you're working on spherical or cylindrical or Cartesian coordinate, like the way we calculate Laplacian should be different, and just make sure it is consistent. Like the coordinate you choose is consistent in your calculation. Okay, so I will not do this in detail since this is your homework problem, but I hope this can help on approaching the problem. What we will instead do in the problem session is we will do the inverse version. So if we have a given density distribution, then how do we obtain the gravitational potential form? All right, so today I will use the singular isothermal sphere density distribution, which is probably also mentioned in the class, right? So singular isothermal sphere. Okay, so for a singular isothermal density sphere, the density distribution should be proportional to the inverse squared of r, right? So that would give us some rho constant and divided by r over r naught squared, where r naught is a constant. And so for the rho naught here, it is also a constant, and this could be related to the spherical density distribution, which is the same as the one in your first problem, but we will use we will assume that the A factor is 0. So the spherical density distribution is VH squared over 4 pi G R. Okay. And okay, let me write this down. This is the spherical density distribution. And this is in homework 3, problem 1 with A 0. Okay. So the reason why I'm relating the rho naught to the spherical density distribution is because we want to show that the gravitational potential of that singular isothermal sphere to be VH squared long R over R naught. And this VH squared over here is like related to the spherical density distribution. So we will use that relation to get in terms of VH. Okay. So, okay, to get the gravitational potential, first we know that gravitational potential is in a form of something like negative GM over R. And to write it down more specifically, it should be negative and integration of G rho dV over X minus X prom and rho of X prom. So this dV can be written as dx prom cubed. Okay, yeah, so this is the most general form of the gravitational potential. And so since now we're dealing with a sphere, of course we will use the spherical coordinate. And this form will give us negative and, okay, so we have the distribution, and so we have G rho over R and dV over here. And we know that for a sphere, dV is simply 4 pi R squared dr, right? And then we can cancel out the R over here and get negative G rho 4 pi R dr, right? 4 pi R dr. And if we plug in, so now we can plug in the given density distribution. And so we will have negative 4 pi G rho. Okay, I'm just writing this again, and the integration should be from R to R0. Okay, so this integration, so the only relevant term should be the R over here, right? Because we're integrating with R. So we can take out all of the terms, 4 pi G R naught, And by plugging in the rho cis, we have rho of R naught taking out, and the integration would be, because there's a R squared, inverse R squared term in rho cis, right? So that would be here, and we can cancel out this. And we know the integral of 1 over R is in the form of ln. So we get negative 4 pi g okay, so as I mentioned, for the spherical density distribution, we have VH squared equal 4 pi g R naught rho naught, right? And which is exactly the same form as we show here. So this term is VH squared. So now we can get negative VH squared and ln R with R naught and R, and that will give us VH squared ln R over R naught, and which is the answer we want. Okay, so any questions for this part? So both the virial problem and the density distribution problem should be, the concept should be very simple, but the more nasty part should be like doing the integral. So if we have a more complicated density distribution, then you should, the integral would be more complicated. So for the homework problems, at least you should write down the correct integral, then you will get most part of the credits, but yeah, but just be careful with the calculation of these integrals.
I have one question.
Yep.
So why isn't it ln of R naught over R when you do the subtraction with the log rules? It's
you mean why isn't
R naught
here?
on top? Yeah, since it's like B minus A. So wouldn't it be R naught over R, or?
Okay, so there's a minus sign here,
Oh,
right?
yeah.
Yeah. So I took off that minus sign. Yeah. All right, so yeah, this is all for today's problem session, and you can ask questions on today's session or on homework problem for the rest time.
I had a question. How did that become VH squared?
Okay, can you hear me now? It seems that I was
Yes.
muted. Okay, great. So VH squared comes from the spherical density distribution I mentioned here. Yeah, so this rho naught is VH squared over 4 pi g R naught, and this is the spherical density distribution. You can see the first problem of your homework. It's the same thing.
Okay, yeah. That makes sense. Thank you.
For the second to last line, how did you could you go over again how you pulled that all out of the integral? Because I get the substituting into VH squared on the last step, but
You
I'm
get,
trying to like, where did you?
uh-huh.
I'm trying to like figure out how you pulled all that out of the integral. The like the p of r naught.
A rho of r naught. Okay, so rho of r naught is a constant. Okay, so that's why we can pull off rho of r naught. And I'll write it more clearly. So, because we are using the given distribution that rho cis equal rho of r naught over r naught squared, right? So we can take this r naught square outside. Oh, this is, I made a mistake. So this should be r naught square. So we take the r naught square outside, and the rho of r naught can also be extract out. So the only terms remaining inside the integral will be the inverse r squared. Does that make sense?
Okay, yeah, I forgot about that definition. Is everything still standing? You just said you made a mistake. Like, did you change anything in the work, or
In the
you just misspeak? Oh, sorry. You just said that you made a mistake. But the work's okay.
I mean, I made a mistake here, but I fixed that already. So I wrote,
Oh,
yeah,
okay.
I wrote r naught, but it should be r naught squared. Yeah,
Okay. Thank you.
no problem.
I just have one more question. What is rho of as a function of r naught? Like, what is that exactly?
Oh, so the spherical density distribution is in the form of rho of r equal, let me see, rho of r equal vh squared over 4 pi g r. So this distribution is a function of r, but since the single isothermal sphere distribution, the rho naught, like the rho naught is like an initial density, so it's a constant, and we relate this rho of r naught with the spherical density distribution at r equal r naught.
I see. That makes sense. Thank you.
And that's how you got VH squared, right? Thank you.
I was curious. So the textbook doesn't really have. At least I can't. Maybe I'm looking in the wrong place, but I don't really see any like worked out problems. Where would be a good place to like? I'm just used to physics textbooks, kind of like going through some example problems so you can see, kind of like this discussion section.
Mm-hmm.
Do you know like if there's any other resources or something, just so I could see like other example problems to know that I'm kind of going in the right direction?
I think there are plenty of example problems in your textbook. So,
Oh, okay. I need to make sure I have the right one then.
Example problem is not enough, or you didn't find the example problem.
I haven't found any yet, but maybe I'm looking in the wrong place. I'm gonna check back in. Okay, never mind.
For the gravitational potential or the gravitation part, is you can find many sample problems under the chapter 3.1. So,
like, are they worked out?
Oh no, they are not worked out. But for most of the problem, they tell you the final form of the answer, but they didn't.
Okay,
show
so you know
the
if you get it.
steps. Yeah.
Okay, all right. I'm gonna start doing those then too. Thank you. Will your office hours be at 7 p.m. Pacific time tomorrow?
Yes.
Okay.
Thank you, Alpha.
Yeah, no problem.
Thank you. Have a good day.
Thanks, you too.